Welcome! In this lesson, we'll study reactions of ions in aqueous solution. We'll learn how to predict precipitates, identify gases, understand acid-base reactions, and write ionic equations. These reactions are important throughout A-level chemistry. A-level specification, scope, and learning objectives. This topic explains how ionic substances behave when dissolved in water and how chemists can use predictable reactions to identify unknown ions. Many ionic compounds dissociate into hydrated ions, surrounded by water molecules through ion-dipole interactions, and that these ions are responsible for the chemical reactivity observed in solution. Dissociation and hydration of ions in water. When an ionic compound dissolves in water, its crystal lattice breaks apart and the ions become surrounded by water molecules, forming hydrated ions. This process is known as dissociation and is fundamental to understanding reactions in aqueous solution. Water is a polar molecule, with a partial negative charge on the oxygen atom and partial positive charges on the hydrogen atoms. As a result, positive ions such as Na are attracted to the oxygen end of water molecules, while negative ions such as Cl are attracted to the hydrogen end. These ion-dipole interactions release energy, known as hydration enthalpy, which helps to overcome the lattice enthalpy holding the ionic solid together. Formation of precipitates from aqueous ions. Precipitation reactions occur when two aqueous ionic solutions are mixed and an insoluble ionic compound forms, appearing as a solid precipitate. The driving force behind precipitation is the formation of a compound with very low solubility in water, meaning its ions prefer to remain in the solid lattice rather than hydrated in solution. Predicting precipitation using solubility guidelines. Solubility rules are a set of general guidelines that help chemists predict whether an ionic compound will dissolve in water or form a precipitate. All nitrates are soluble, meaning that compounds such as sodium nitrate and copper, nitrate always dissolve to give aqueous ions. Most sulfates are also soluble, but there are important exceptions, notably barium sulfate, lead, sulfate, and calcium sulfate, which are insoluble or only very slightly soluble. These exceptions are crucial in qualitative tests, such as the use of acidified barium chloride to test for sulfate ions, where a white precipitate of BaSO confirms their presence. Hydroxides provide another important set of rules. Most hydroxides are insoluble, but those of sodium, potassium, and calcium are soluble or slightly soluble. This explains why adding sodium hydroxide to solutions of transition metal ions often results in colored precipitates. Writing, balancing, and interpreting ionic equations. Ionic equations provide a clearer picture of what is actually reacting in aqueous solution by focusing on the ions involved. To write an ionic equation, all strong electrolytes are shown as their constituent ions, while solids, liquids, and weak electrolytes are written in molecular form. For example, in the reaction between aqueous lead, nitrate and potassium iodide, both compounds dissociate fully, so Pb squared, NO, K, and I ions are shown. The precipitate, lead, iodide, is written as a solid. Once the full ionic equation is written, spectator ions, those that appear unchanged on both sides, are cancelled to produce the net ionic equation. Using sodium hydroxide and ammonia to identify cations. Sodium hydroxide and aqueous ammonia are used as reagents to form metal hydroxide precipitates with characteristic colors and solubilities. For example, adding a few drops of sodium hydroxide to a solution containing Cu² ions produces a pale blue precipitate of copper, hydroxide, which is insoluble in excess NaOH. In contrast, aluminium ions form a white precipitate of UlOH, which dissolves in excess NaOH due to the amphoteric nature of aluminium hydroxide. Iron ions provide another clear distinction. Fe² forms a green precipitate of iron, hydroxide, which slowly turns brown on standing due to oxidation, while Fe³ forms an immediate brown precipitate of iron, hydroxide. Aqueous ammonia can give different results, helping to distinguish between ions such as Cu², where the blue precipitate dissolves in excess ammonia to form a deep blue complex. Tests for halides, sulfates, and carbonates. Halide ions are identified using silver nitrate solution after acidifying the sample with dilute nitric acid to remove interfering carbonate ions. Chloride ions produce a white precipitate of silver chloride, bromide ions produce a cream precipitate of silver bromide, and iodide ions produce a yellow precipitate of silver iodide. Sulfate ions are tested using acidified barium chloride solution, forming a white precipitate of barium sulfate if sulfate is present. Acidification is crucial because it prevents false positives from carbonate ions, which would otherwise form barium carbonate. Carbonate ions themselves are tested by adding dilute acid and observing effervescence due to carbon dioxide gas, which can be confirmed by turning limewater milky. Proton transfer and neutralization in aqueous solution. Acid-base reactions in aqueous solution are best understood in terms of proton transfer, as described by the Bronsted-Lowry theory. Acids donate protons, H ions, and bases accept protons. In aqueous solutions, hydrogen ions are hydrated and often represented as H, Ac, for simplicity. Neutralization reactions occur when H ions react with hydroxide ions to form water. Electron transfer involving aqueous ions. In aqueous solutions, redox processes often involve metal ions gaining or losing electrons. Oxidation is defined as loss of electrons, while reduction is gain of electrons. For example, when iron 2 ions are oxidized to iron 3 ions, they lose an electron. Conversely, halogen molecules such as chlorine can be reduced to chloride ions by gaining electrons. Predicting feasibility of ionic redox reactions. Standard electrode potentials, measured under standard conditions, indicate the tendency of a species to be reduced. By comparing E-degree values, students can predict whether a redox reaction is feasible. For example, a species with a more positive E-degree value is more likely to be reduced. Carrying out qualitative tests accurately and safely. Practical competence is a vital component of chemistry course, and reactions of ions in aqueous solution provide many opportunities to develop these skills. Students must be able to carry out qualitative tests methodically, using clean test tubes, adding reagents dropwise, and recording observations carefully. Safety is also essential. Eye protection should be worn, acids and alkalis handled with care, and waste disposed of according to laboratory guidelines. Using observations, tables, and charts in analysis. Although qualitative analysis often focuses on observations rather than numerical data, students are still expected to present and interpret results clearly. Tables are commonly used to summarize observations for different reagents, making it easier to compare outcomes and identify patterns. Charts and diagrams can also help visualize processes such as precipitation or hydration. Avoiding errors in qualitative and ionic analysis. Students often make avoidable mistakes in this topic, such as confusing precipitate colors, forgetting to acidify samples, or omitting state symbols in equations. Another common misconception is believing that the original compound matters more than the ions present in solution. Applying knowledge effectively in A-level assessments. Always learn the key solubility rules, memorize common ionic equations, and remember the tests for important ions. Practice writing ionic equations regularly. Connections to other A-level chemistry topics. Acid-base reactions link to pH calculations and buffer solutions, redox reactions connect to electrochemistry, and solubility rules provide a foundation for equilibrium concepts such as KSP. Recognizing these links supports synoptic understanding. Key takeaways for reactions of ions in aqueous solution. In aqueous solutions, ions react to form precipitates, gases, or water. Understanding these reactions helps explain many practical laboratory tests and chemical processes. You should now be able to predict reactions in aqueous solution, write ionic equations, identify spectator ions, and recognize the tests for common ions. These are key skills for success in A-level chemistry. Thank you for watching.